On New Year's Eve, December 31st, 1940, a Vickers Wellington bomber cruised through heavy snow squalls at 8,000 feet above the Scottish Highlands. The aircraft, designated N2980, was piloted by squadron leader Marwood Elton on a navigation training exercise. The mission profile was routine, but the meteorological conditions were deteriorating. Without warning, the starboard Bristol Pegasus engine lost power. The failure was immediate and irreversible. The aircraft, heavy with fuel and now down one engine, lacked the thrust to hold altitude. It began a forced descent. The pilot faced a binary decision matrix dictated by the terrain below. The mountains south of Loch Ness, the Mauna Lea area, offered granite peaks and deep ravines, a landscape where a forced landing could mean airframe destruction and fatal odds for the crew. The standard procedure for such a scenario is a bailout order. Marwood Elton followed the protocol and commanded the crew to jump. However, as the aircraft dropped through the cloud base, the operational picture shifted. The long, dark expanse of Loch Ness appeared through the snow. The presence of a flat water surface introduced a second option. A controlled ditching offered better odds than dropping by parachute into that storm over rock. He snapped the bailout order back and shouted for the crew to stay at their stations for a water landing. This reversal of command, while operationally sound, created a fatal timing error for one man. Sergeant Fensom, the rear gunner, had already initiated his egress sequence. He left the aircraft moments before it leveled off for the ditching. His parachute failed to open. He fell to his death, the single fatality of the incident. The remaining crew braced for impact. Marwood Elton executed a textbook ditching on the surface of the loch. The Wellington, despite its size and drag, settled onto the water without breaking apart. The fuselage remained buoyant for a critical window of time, allowing the pilot and co-pilot to escape through the overhead ditching hatch above the cockpit. They deployed a dinghy and paddled for the nearest shore, close to the A82 road. Behind them, the bomber took on water, the nose dipped, and the airframe slipped beneath the surface. It descended through the cold, freshwater column and came to rest on the bottom. For more than 3 decades, the aircraft effectively vanished, surviving only as rumor. Loch Ness is deep and peat-dark. Its silty floor swallows wreckage and erases detail. N2980 lay 70 meters down, out of reach, sealed in cold water that would later explain what endured. The status of the wreck changed in 1976. A team led by Martin Klein and Robert Rhines arrived at the loch with a different objective. They were not looking for aluminum or history. They were investigating reports of unusual large aquatic creatures. The kind of mission that made Loch Ness famous. Their primary sensor was side-scan sonar. During a sweep of the northern basin, the equipment registered a contact that violated the natural pattern of the lake bed. The return was not organic, it was geometric. The sonar image showed a distinct, angular shape with a high aspect ratio, sitting upright on the sediment. Analysis of the sonar data, followed by underwater camera work in subsequent years, confirmed the identity of the target. It was the missing Vickers Wellington. The discovery was significant not just for its location, but for the specific history of this airframe. Records confirm that N2980 was a veteran of the Battle of Heligoland Bight, a disastrous early war raid that had shaped Royal Air Force daylight bombing doctrine. It was the only surviving example of its type with combat history. The aircraft was largely intact, a time capsule sealed in the cold mud. The location was now verified, but the transition from a sonar target to a recovered artifact presented a massive engineering challenge. The aircraft lay at a depth of 230 feet. At this depth, the pressure is high and the darkness is absolute. The evidence suggested the airframe was whole, but the structural integrity of a fabric-covered skeleton after decades of immersion was an unknown variable. The objective was clear: lift the bomber. But the constraint was the environment itself, which had held the plane safe for half a century and would not easily let it go. The structural integrity of the Vickers Wellington is defined by a geometry that does not exist in modern aviation. Most aircraft are built as a semi-monocoque tube, where the skin carries a significant portion of the structural load. The Wellington, however, is a basket. Designed by the engineer Barnes Wallis, the airframe utilizes a geodetic lattice construction. Thousands of aluminum alloy beams are screwed together in a spiraling, crisscross pattern to form the fuselage and wings. This design creates a redundant network where every member shares the stress of flight and gravity. This unique architecture is the primary reason the aircraft survived the violence of its arrival in Loch Ness. When a conventional airframe strikes water at landing speed, the deceleration forces are asymmetric and brutal. Water acts as a solid barrier against the thin metal skin, often causing the fuselage to buckle or snap at the point of highest stress. The geodetic lattice behaves differently. Upon impact with the surface of the loch, the woven aluminum structure flexed. The energy of the collision was not concentrated on a single failure point, but was distributed instantly throughout the entire web of the airframe. The lattice absorbed the shock of the 86-foot wingspan hitting the water, dissipating the kinetic energy that would have shattered a stiffer machine. This energy management allowed the bomber to remain intact, protecting the crew during the ditching and preserving the aircraft as it sank. For 45 years, the bomber sat in the silence of the deep trench, and time moved strangely slowly. The aluminum framework endured far better than anyone would expect, while the doped Irish linen skin, an organic layer, rotted and slackened, peeling away in places and exposing the skeleton. As the linen rotted away, the bomber stopped being a smooth, sealed shape and became a snag field. Thousands of open bays and proud screws waiting to catch whatever drifted past. Over the years, fishing nets and lines were dragged across the loch bed and lost. When they met the Wellington, they didn't slide off, they bit in. Surveys found wing and tail sections fouled by old netting, adding drag and unpredictable weight, and worse, tying the fragile frame into the surrounding silt. Try to lift it without clearing those snarls and the nets become anchors, turning vertical lift into a tearing pull that could rip the tail from the fuselage. Loads the lattice was never meant to take at a single, brutal point. The final variable was the sediment itself. The Wellington sat with its wheels sunk and its belly partly buried, the silt sealing around it like a gasket. Before any lift plan could make sense, the team had to understand exactly what the loch floor was holding, and how hard it would refuse to let go. Reading a side-scan sonar run means thinking in echoes, not images. The towed transducer paints the bottom in contrast. Hard returns, bright, soft silt, dull, while shadows hint at height and form. In 1976, the paper trace showed a sharp, high-profile return where the lake bed should have faded to blank, its edges too straight to be natural. Even then, it was still only a shadow. However, an acoustic shadow is not positive identification. Confirmation required a visual survey. In the late 1970s, underwater camera work began to turn the sonar contact into something real. By 1981, the operation added a remotely operated vehicle, an ROV, able to reach 230 feet with cameras and lights, and to linger on the bottom far longer than a working diver ever could. The video feed finally put eyes on the target. The camera lights washed over the unmistakable basket weave of the geodetic structure. The doped linen fabric, while degraded, still covered large sections of the fuselage. Distinct markings were visible. The aircraft's individual letter, R for Robert, matched the records for Wellington N2980. This was not just a generic Wellington bomber, it was the exact airframe lost on that New Year's Eve flight. The survey proved that the aircraft was upright and largely intact, rejecting the theory that it had broken its back upon impact. The combat veteran was verified. The survey also revealed the extent of the contamination. The ROV inspections mapped the location of the fishing nets detected by the sonar. The video showed thick trawler nets draped over the starboard wing and the tail section. These were not loose debris. They were entangled deep within the open lattice of the geodetic framework. The nets were heavy, waterlogged, and buried in the silt. They effectively shackled the aircraft to the bottom. This discovery defined the boundary of the recovery operation. The lift could not even begin until the aircraft was freed from what was tying it to the bottom. The survey data dictated that the nets had to be cut away by hand. Furthermore, the survey showed that the fabric skin, while present, offered zero structural strength. It could not be used to contain lift bags. The lift points would have to be attached directly to the primary structural members of the lattice. The survey boxed the problem into hard facts: a fragile airframe, pinned by mud and bound up in nets. From here on, every move would be slow, deliberate and limited by what humans could safely do in the dark. At that depth, cold, darkness, and decompression turned every minute into a penalty, forcing a slow rhythm, careful rigging, short dive windows, and constant remote watching. The primary task for the diving team was to rig the aircraft for the lift. A direct connection to the airframe was impossible. The geodetic lattice is strong, but it is designed to handle aerodynamic loads distributed across the entire structure, not the concentrated point load of a steel cable. If a cable were wrapped around the fuselage and tightened, the inward crushing force would buckle the aluminum ribs. To solve this, the engineers employed a spreader bar system. A spreader bar is a rigid beam positioned above the load. It holds the lifting slings apart at a width equal to or greater than the object being lifted. This geometry ensures that the cables pull vertically rather than diagonally. By eliminating the horizontal component of the tension, the crushing force is neutralized, and the aircraft is subjected only to vertical support. The recovery plan called for a massive rectangular lifting frame to be lowered over the Wellington. The divers in the suits had to tunnel through the silt beneath the fuselage to pass wide nylon straps under the belly. These straps would then be connected to the frame, cradling the bomber like a toy in a sling. But before the aircraft could move, the team had to overcome the physics of mud suction. When an object rests in deep silt, it displaces the water between itself and the bottom. Over decades, the Wellington had settled, squeezing out the water and creating a seal. To lift the aircraft, water must flow back into that space to equalize the pressure. If the lift force is applied too rapidly, a vacuum forms beneath the hull. The entire weight of the water column above acts down on the aircraft, clamping it to the mud. This suction force can be orders of magnitude greater than the actual weight of the object. The lifting gear had to be capable of exerting enough steady tension to slowly break this vacuum without snapping the airframe in half. The operation launched with a custom-built steel lifting frame. The frame was deployed, and the divers began the arduous process of rigging in the zero-visibility silt cloud. Tension was applied to the system. The gear took the load of the aircraft plus the immense resistance of the mud seal. Then the equipment failed. The lifting frame, designed to support the bomber, buckled under the stress or was damaged during the complex deployment. The steel collapsed, twisting into a useless shape. The failure was total. The frame was hauled to the surface, a ruined skeleton of metal. The Wellington remained on the bottom, still in the grip of the sediment. The project had lost its primary tool. With the weather window closing and the budget draining away, the engineering team faced a timeline crisis. They had only days to solve a problem that had just destroyed their heavy equipment. With the primary frame gone, the team faced a blunt choice: stand down for the season or build a replacement immediately. The weather was turning and the budget was bleeding out. There was no time for factory precision. They chose speed, sketching a simpler, stronger frame on the back of an envelope and betting on raw steel and clean geometry. The fabrication took place at a facility on the Murray Firth. The new structure was a robust assembly of steel beams built to exceed the safety factors required for the lift. It lacked the complex articulation of the failed unit, relying instead on rigid geometry to maintain the spreader bar principle. Within days, the new frame was transported to Loch Ness and lowered into the dark water. The atmospheric diving suit pilots returned to the bottom, working through the silt to reattach the nylon slings. The process of threading the straps under the fuselage had to be repeated, with the divers ensuring the load would be taken by the main spars of the geodetic lattice, avoiding the weakened fabric sections. On September 21st, the lift sequence initiated. The crane barge on the surface began to take up tension. The cables tightened, transferring the load to the submerged frame. The critical phase was the breakout from the sediment. The mud suction, which had held the aircraft for 45 years, acted as a final anchor. The operators applied tension gradually, avoiding a sudden jerk that could shock load the aluminum skeleton. Slowly, the adhesion yielded. The tires pulled free from the silt, and the water rushed in to equalize the pressure. The Wellington was airborne once again, rising through the water column at a controlled rate. As the aircraft ascended, the hydrostatic pressure decreased, and the hydrodynamic drag increased. The structure, designed to fly forward at speed, was now being lifted vertically, a vector it was never built to endure for long. Even with a controlled rise, fittings and stressed joints could begin to give way. Some components were at risk of loosening or detaching as the bomber approached the surface. The lift pressed on, prioritizing the survival of the main airframe. The aircraft broke the surface near the Bana lighthouse. For the first time since 1940, the silhouette of N2980 was visible in the daylight. The water drained from the fuselage, cascading out of the open lattice. The weight of the aircraft increased momentarily as it transitioned from the buoyancy of the water to the full pull of gravity, but the new frame held. The Pegasus engines, each capable of generating 1,050 horsepower, hung heavy on the wings, their propellers bent from the initial ditching impact. The fabric skin was tattered, revealing the interlaced geodetic lattice beneath, but the bomber's shape was unmistakable. The recovery was a validation of the field engineering decision. The aircraft was lowered onto a waiting barge, secured, and prepared for transport. The physical extraction was complete. The mud had been defeated, and the lattice had held together. However, as the team inspected the dripping airframe, the focus shifted from the heavy engineering of the lift to the forensic details inside. The aircraft was not just a structure, it was a system of circuits and switches, one of which was about to provide a final, unexpected piece of evidence. One of the strangest clues about the aircraft's condition did not come from a lab. It came from a simple test on the dockside. When the team connected a modern battery, the Wellington's navigation lights still worked. This anomaly was not a miracle, it was a demonstration of specific environmental chemistry. The preservation of the aircraft was the direct result of the water composition in the loch. In a saltwater environment, the ocean acts as a highly conductive electrolyte. When aluminum alloys and dissimilar metals like copper wiring are submerged in brine, they form a galvanic cell. The resulting corrosion is rapid and destructive, often converting an airframe into a pile of unrecognizable oxide within decades. Loch Ness presents a fundamentally different chemical profile. The water is fresh, significantly reducing its conductivity. Furthermore, the depth of 230 feet ensures a constant low temperature, slowing the rate of all chemical reactions. The peat suspension in the water blocks sunlight, preventing organic growth that would otherwise colonize and consume the wreckage. When the bomber sank into the silt, it entered a cold, dark, freshwater environment where decay and corrosion could be dramatically slowed. This environment arrested the aging process of the inorganic components. The rubber insulation on the wires, the glass of the bulbs, and the duralumin of the geodetic lattice remained stable. The only major casualty was the organic, doped linen, which had decayed naturally over the decades. The recovery of N2980 presented the Brooklands Museum with a complex curatorial decision. Standard aviation restoration practice in the 1980s often involved stripping an airframe down to its component parts, treating corrosion, and rebuilding it to a factory-new appearance with fresh skin and paint. This approach creates a pristine display, but it erases the history of the artifact. It hides the damage, the wear, and the unique engineering that defines the machine. The conservation team chose a different path. They recognized that the value of R for Robert lay not just in its identity as the only surviving veteran of the Battle of Heligoland Bight, but in its construction. The geodetic lattice designed by Barnes-Wallis is a masterpiece of structural efficiency, a complex weave of metal that is usually hidden beneath fabric. To skin the aircraft would be to obscure the very feature that allowed it to survive the ditching and the lift. The decision was preservation, not a factory-new rebuild. The airframe was cleaned and stabilized for display, with broad sections left open so visitors could see the geodetic lattice itself, not a flawless, reskinned replica. The display also serves as a permanent record of the loss event. The damage from the ditching is visible. The missing nose turret, recovered separately, tells the story of the extraction forces. The empty rear turret stands as a silent acknowledgement of Sergeant Fensom, the flight's lone loss when his parachute never opened. The aircraft is not presented as a triumphant war machine, but as a forensic document of a specific operational failure and a successful survival sequence. Today, N2980 stands as a validated proof of concept for deep-water aviation archaeology. The operation demonstrated that a fragile, complex structure could be retrieved from a high-suction environment if the engineering physics are respected. The back of envelope lifting frame, the use of atmospheric diving suits, and the patience of the survey team resulted in the preservation of a unique class of aircraft. The light that turned on at the dockside was more than a curiosity. It was the final signal that the loch had surrendered its prisoner intact.